This is problem 117 of Neetcode 50, longest increasing path in a matrix. So we're going to be given a 2D matrix, and each integers will be greater than 0. We're going to have to return the longest path of values that are strictly increasing, so we can't have values that are of the same values. We can move horizontally and vertically, but we can't move diagonally. So if we take this example 1, we can see that from the 5, we can go to the right because it's a value that is equal to its own value, and we can go down because it's the value 2, which is smaller. Can go diagonally and to the left and to up. We basically have nothing. We're out of bound. So this value has a longest path of 1. And holistically speaking, if we take a look at this path, we can see that if we go from the 1 to the 2 to the 3 to the 6, we have basically a length of 4. That's the length of the path. We have 4 cells making up this path, and this is strictly increasing. So I will show you how I will solve this problem today. So I have the exact same path as the one I had in my example, or the exact same grid, I will rather say. And what we're going to do is that we're going to figure out at each cell what is the longest path from that very cell. And we will do this by using depth first search. So let's go ahead and do this. So we're going to start basically by doing some top-down work. So we're going to get the 5 here, the top left cells. And what we're going to check is that we're going to go see its neighbors. So we're going to go see the 2 here. We're going to go see the 5 here. And basically, if the value is not greater than that previous value, we're just going to return a 0 because we won't have a path that is strictly increasing. And also, a cell by itself is also a path of length 1. So what we're going to put in our grid is basically a 1 here because we know that we can't go any farther with our neighbors. So we're going to put a 1. And similarly for this 5 here, if we take a look at all its neighbors, so yeah, you're going to have a 5 here, you're going to have a 3 here, you're going to have a 3 there. Well, none of them are actually greater. So once we throw once we call a depth first search on each of them, you'll see that none will pass, and we'll be left up with that single cell by itself. So it's going to be a 1. But now here comes the interesting part. When we reach that value 3, if we go to the left, we have a cell that its longest path has already been found, right? So we found that it is a 1. So, okay, this is good. Now if we go down, we have another path, and this path is valid because the value 6 is greater than this previous value 3. So it's worth actually considering. So what we're going to do is that we're just going to go for a second at this cell, and we're going to call depth first search on it. So this cell is going to go see all its neighbors. Yeah, it's going to go see its previous cell back, but since the previous cell is smaller, it won't really be considered. So it's just going to go see its neighbors, but all its neighbors are smaller. So at this place with the value 6, we're just going to put a 1 here. And once we have a 1, we're going to go back to our cell tree, and we're going to ask ourselves, among all my neighbors, what is the greatest path, or the longest path, rather, I can have. And right now we have a tie, right? Both cases, like the case to the left and the case that is down to itself, is basically has the greatest length of 1. So what we're going to do is that we're just going to add 1 to this because this cell actually counts. So we're going to have like a path of length 2 here, and we have another path of length 2 here. So we're just going to add a 2. And now we are going to keep our search going. So we're going to go see this value 2, and we'll realize that it has 2 values in its neighborhood that are greater than itself. So we're going to go see them. But notice that the 5's greatest length has already been solved. So we know that along this path, our longest path will be of length 2, because it's going to be this cell 1 plus the greatest path up there, which is going to be 2. But we didn't find yet the greatest path from this tree. So if we go to this tree, we see that we have a value that is greater than this tree to the top, a value that is greater than this tree to the right. Okay, and in this case, um, both values longest path have already been solved, which is 1. So the longest path that we can have from this 2 is basically going up, or it is to go to the right with this cell. And in both cases, we have a path of length 2. So we're just going to put a 2 here. And now back to our 3, our 2. We are still going to look at the value that is up and the value that is right. And we can see that the longest path we can currently make, well, it's going to be of length 3, right? Because it's going to be itself plus the path to the right. So we're going to have basically a path of length 3 in this way. So I'm going to put a 3 here. And now my top-down search is still going to go see the next value. So we're going to go see the 2, but the 2 is already has already been seen. So we're just going to create a hash map to keep track of the values. And then we're going to do the same thing here. We're going to go see this 6, but this 6 has already been solved. So we're just going to pass on. And now we're going to go see this 1 value. And at this 1 value, we're going to go see the value that is up, the value that is to the right. We're also going to see what is down and what is to the left. But notice that what is down and what is to the left is basically blank space. And that the value to the right is the same value of itself. So it's not going to count. So the only value we really care about is going to be the value to the top. And we already know that the greatest path starting from the value to the top is 3. So we're just going to add 1 plus this 3. And we know that the greatest path starting from this one is going to be 4. Right? And when we go to this one here, we're going to go see all its neighbors. We're going to realize that the only greatest value that can form a strictly increasing path is the tree that is up here. And the tree value up there as a path that has already been solved. So we're just going to add a 1 to this value. So we're going to have path of 3 starting from here, and finally from this value 1 here, the only greatest value we can have so far, we can have by seeing our neighborhood, it's going to be the value that is above, which has an absolute greatest path of 1. So we're just going to add 1 to this absolute greatest path. So it's going to give us 2. And now realize that if we just say max of all this thing, we're going to add the greatest value, which is 4. And this is going to represent basically this path, which is what we had in our example. So this is what we're going to do to solve this problem. First of all, I will create a variable row and call. And the row is going to be just the length of the row. So the length of the rows is going to be the length of the matrices, and the length of the column is the length of a single row. So it's going to be the length of matrix, and I will take the index 0 for this. Now I will create a hash map to keep track of the greatest path of each cells, and also to ensure that we don't create unnecessary depth first search calls. So after this, I can create my depth first search function. And in this, I want to pass the row. I want to pass the column that we're at. And I also want to pass basically the previous value, as we have to compare its absolute value with the current cells we are at. So what I will do is that I will first add my first preliminary check. So first I want to see if we are either out of bound in the negative value. So either R or C is smaller than 0. This is not good. Or basically if the R is equal to rho, this means that we are also getting out of bounds. Or if the column is equal to, if the C is equal to call. Okay. And the third case is that if the previous value is greater or equal than the value we are at, well, it means that the path right now is not increasing, it's actually decreasing. So we're gonna have to act upon it. right? So these are all the cases we where basically we can continue along this path. So in this case, we're going to return a 0 because we can't go any further. Now, what if our neighbor has a value that has already been seen? So if R and C is in DP, then we're going to be willing to return the value of that DP if it has been calculated. Because if it is in DP, it means that its longest path has already been calculated. So we're just going to return that. So for C, so we're going to return this, and this is going to return its value. Right now, we can actually create a part where we're going to go see all the neighbors and basically put in our hash map at this position, the longest path, by considering all its neighbors' longest path. So we're initially going to create a results variable that is equal to 1, because we know that in the worst case, but that self itself is going to be of length 1. So this is what we're going to be placing inside our hash map at this position. And now I will have a couple max statements, and in each of them I want to compare the previous results, and I want to compare basically the path that I can take starting from the current cell I am at plus its neighbors. So I am placing a 1 here, which represents the current cell's values, and I want to basically set a call to its neighbor to the right, its neighbor to the left, its neighbor that is up, and the one that is down. So to do so, I will just have a couple call like that, and I will copy this. I will paste that for three more times, and then I want to update the actual. Oh, seems like I press on submit. All right, I apologize for that. So first thing I want to do is that I want to go to the right. So I want to add 1 to my column, and I want to go to the left then. So I'm going to decrement my column by 1. Then I want to go down, so I'm going to increment my row by 1. And I want to go up, so I want to decrement my row by 1. And then I know that the result variable is going to hold the actual longest path for that cell. So I can set the DP at that row and at that column to be equal to the result. And then I can return the result. For each call, I want to return this. So that's good enough. That's pretty much all we need for the depth first search function. Now we're going to go for every single cell, going top down, and we're going to call our depth first search on it. So I'm going to say for each row. So for R in the range of row, and for C in the range of call, I will create my DFS on it. And what I'm going to pass for the previous value is just a dummy value. I'm going to put -1, could be -10,000. Doesn't matter as long as it is something smaller, because we know that like the previous value is going to be obviously, well, like a cell from the matrix, and we know that the matrix only contains values that are equal or greater than 0. So you can really put like whatever you want there. It can be something random as long as it is not a positive value that could potentially be in a matrix. So this should work, but for aesthetic reasons, I will just put a -1 here. So now after these calls, well, we know that the greatest value is somewhere inside the values of this DP, so I can simply return the maximum value in dp.values. Right, so by doing so, I will basically get that 4 in our example, and we can test this out. I made an error here. Let's do this again, and it works. So in terms of space complexity, I think it is quite obvious because we're creating a hash map for basically the length of the 2D grid, right? So every cell has its key and its values inside the hash map. So we're gonna have a space complexity of big of m times m, where m is the number of row and n is the number of column. And the time complexity is also going to be big of m times n, because we're gonna go one cell at a time in our 2D grid, and we're never gonna recalculate another values. So even though we're calling depth first search on its neighbors, well, by doing so, we're also calculating its neighbors' values. So then when we come back to it, we don't actually have to recalculate them. So we're just gonna calculate each values, uh, each values one. So this is why it is gonna have a time complexity of big of m times n, where m is the number of row and n is the number of column. With that being said, I hope you enjoyed this video. I hope you learned, and I hope to see you in the next one.